everyone, in this video we're going to revise AS Organic Chemistry and we're going to do that through past paper questions. Now you can find the link to download the PDF of this set of past paper questions. It's in the link in the description below and you can have a go at them by yourselves first and then use this video to mark them, or we can do them together. So the first question, which statement is correct for the two structures below? They have the same empirical formula. So to do this, we need to count up the number of carbons and hydrogens for each of these. And you might wish to draw on the carbons and hydrogens so you can see them properly since it's skeletal. So here we've got a carbon. We know that every carbon has 4 bonds. So we draw on the other 2 bonds which go to hydrogens, and we just don't show those in skeletal. Then here we've got a methyl group and so on. So you might wish to do that. I mean, you can see the answer here, but we'll go through the others. They have different relative molecular masses. So if you were to add up your carbons and hydrogens using the mass numbers from the periodic table, you'd find that they've got the same molecular mass. Structural isomers, they're not. They are exactly the same, just rotated, just flipped. Different functional groups, no, exactly the same. An alkene on both, so it has to be A. Next question, which property explains the low reactivity of alkanes? When a question is asking about low reactivity, it's nearly always to do with a high bond enthalpy. So if it takes a lot of energy to break the bond, then it's not likely to react, or it will do that a lot more slowly. Third question, what are the correct reagents? So reagent is just something that we add to a reaction, like a reactant, to do the conversion below. So we're changing an alcohol into a halogenoalkane. And to do that, we need halide ions in acidic conditions. So we need a sodium halide and sulfuric acid. So the correct answer is C. Next question, what is the systematic name of the compound below? So to do this, we need to find the longest carbon chain first, and we start counting the carbons from the alkene. We want to give the functional groups the lowest possible number. So we start here, it's carbon number 1, and we count along to carbon number 6. So it's got to be a hex. We've got an alcohol group, so it's going to end in -ol. The alkenes between carbon 1 and 2, so we say it's on carbon 1 because we want that lowest number, so it's either B or D. The alcohol, that is on number 3, so it's still either B or D, and the methyl group is on carbon number 4. And it's a methyl group, not an ethyl, so it has to be B. What is the number of unsaturated isomers? So that means isomers with a carbon-carbon double bond that have this molecular formula. So to work this one out, it's recommended that you draw the isomers, and the correct answer is 4. What do curly arrows always show in reaction mechanisms? It's the movement of a pair of electrons. It's not a lone pair because sometimes it's a bonding pair. For example, if we're breaking a bond, it's not the movement of one electron because that is a half arrow or a fishhook arrow. And it's not always movement of electrons in a covalent bond either, but it is always this one. The repeat unit of an addition polymer is shown below. What is the monomer? So to get the monomer from this, we just draw a double bond in between these carbons. I've drawn the displayed structure so we can see it properly. Then we just need to convert that back to the skeletal and figure out which one of these it is. So we've got the carbon-carbon double bond on the left-hand side at the end. Then we've got another carbon-to-carbon bond and the alcohol, so it has to be A. This question is about unsaturated hydrocarbons. 2 reactions of propene are shown below. In the boxes show the structures of the organic products. So the first one, polymerization, we get rid of that double bond and we just show one repeat unit. So we've got our hanging single bonds on the end, and these are just where they were before. Then we're adding hydrogen bromide, and that adds across the double bond, which changes that double bond to a single bond. And the hydrogen and bromine, they can add in two different places, so we can get two products. Propene also reacts with bromine. Outline the mechanism for the reaction. Show curly arrows, relevant dipoles and products, and it's worth 4 marks. Firstly, this mechanism is electrophilic addition, and the bromine molecule is the electrophile. So what happens as this bromine approaches this alkene? The electrons in this carbon-carbon double bond start repelling the electrons in the bromine-bromine bond. So the electrons get repelled by these ones in the double bond and then move towards this bromine that's further away. That gives this bromine a delta positive charge and this bromine a delta negative charge. We always draw arrows from the electrons to the electron deficient center. So the arrows coming from our double bond. So we should make it more clear that that arrow is coming from the middle of that carbon-carbon double bond, really. Ugh, made a mess of that. So this is forming a bond now to that bromine, and that causes this bromine-bromine bond to break, and this leaves as a bromide ion. So we normally get 1 mark for each of these curly arrows. So then we form our carbocation intermediate. That's a compound with a positively charged carbon, and this is a reactive center. That bromide that's hanging around from here, it's going to attach to this carbon and form a bond. And the product, that is our final mark. The next question is asking about radical substitution, and it says what is meant by a radical, and that is just a species with an unpaired electron. And the type of bond breaking that occurs in radical substitution is homolytic fission. So fission means breaking, homolytic means one electron from the bonding pair goes to each atom. And to show that, we do fish hook arrows. So from that bonding pair, one electron goes onto each of the chlorines. That's homolytic fission. Whereas heterolytic fission would be, for example, both electrons going to one bonded atom. So that's an example of heterolytic, and that would be homolytic. In this reaction with bromine, monosubstitution of alkane A forms a mixture of organic products. Show the structures of 2 monosubstituted organic products that are formed. Monosubstituted means that one substitution has taken place. So in other words, one bromine atom has replaced one hydrogen atom. And we need to know that the bromine can replace any hydrogen on this molecule. So it can replace this one, or it can replace any of the CH3s. And there's 1 mark for each product. Next, with excess bromine, further substitution takes place. When we see excess bromine, that just means 2 lots of the bromine. If it was an oxidation with alcohols and it said excess, it would be 2 lots of the oxidizing agent as well. So just thinking organic at A level, excess means 2 lots. Write an equation for the reaction of alkane A, that's this one, with excess bromine to produce 1,3-dibromo. So that's telling us the positions of the bromine atoms on the carbons. 2-methyl, so it's got a methyl group on carbon 2, propane, so it's a 3-carbon chain. So we draw that product. Here's our carbon chain, 1, 2, 3. There's our methyl on carbon number 2 and our bromines on carbon 1 and 3. And we have a side product as well, 2HBr. And we can figure that out just from counting our atoms and seeing what's left. So we get 1 mark for the product and the 2nd mark for the full balanced equation. The next question is about practical techniques, and it's a reflux diagram, and it wants us to label it. So name of technique, this is reflux. It wants us to label this bit, that is a condenser or Liebig condenser, At the bottom, water comes in from the tap and water goes out at the top. So that pipe, we have a pipe there and it carries the water back down the sink. And we have, this is a pear-shaped flask. So the other option is a round bottom flask, but the one in this diagram is pear-shaped. And we get 1 mark for the correct water flow, so in at the bottom, out at the top, and condenser labelled. And our second mark for the correct flask, pear-shaped, and naming the technique correctly, reflux. This next question is about branching and forces. So which structural isomer of this has the weakest London forces? It's going to be the most branched one, because these molecules can't pack as closely together, so their intermolecular forces are weaker. So the correct answer is D. Now this question I've labelled as an extension. It is from an A2 paper, but curly arrows is AS knowledge. So we're using our understanding of curly arrows and applying it to unfamiliar examples. Carboxylic acids, sulfonic acids, esters, we might not have met these in AS, but we can still have a go at this question. So it's telling us that the hydroxide ion acts as a nucleophile. That means the lone pair on the oxygen is going to attack the delta positive sulfur. And it's like a spot the difference. If we're not sure what's happening, we look at this and we look at what's changed over here. So we can see we've got a sulfur oxygen double bond here on the left, but a sulfur oxygen single bond here on the right. That double bond has to break. But if we look over here again, it's got to reform. So we can see we've also got a lone pair that's been drawn and a negative charge that's appeared as well. So I'm going to make my arrow coming from the electrons in the double bond, going onto the oxygen. That's going to form that negative charge. Then over here, we need to reform that double bond. So I'm going to do my arrow from the lone pair of electrons and the negative charge to that sulfur oxygen single bond to reform that double bond. And we can see that that OCH3, that's disappeared on this one. So that bond needs to break. And I'm going to do my arrow from the sulfur oxygen bond onto the oxygen. Then in the next diagram, we can see we're going from this to a single bond oxygen with a negative charge. So this bond needs to break, and we can see that this here becomes methanol. So it's just drawn a bit strangely, but that is methanol. So in order for this to happen, this is acting as a nucleophile. I'm showing the electrons coming from the lone pair on the oxygen, picking up that hydrogen to form methanol, and in doing that, that causes the electrons from the OH bond to go onto the oxygen to form this negative charge. So we get 1 mark for 3 correct arrows, 2 marks if we have 4 arrows correct, 3 marks for 5 arrows, and 4 marks for all 6. Now this question I've labelled as an extension, but it is from an AS paper. It's just quite a long and tricky question, and there's a lot to look at. So we've got an organic liquid and it gives us a boiling point. It's telling us it prepares this liquid by reacting an alcohol with concentrated hydrochloric acid, and the first thing it does is ask for a balanced equation using skeletal formulae. So if you want to draw displayed formulae first up here, just so you can see what's going on, and then convert it to skeletal, that's absolutely fine. But we should end up with this. So the only thing that's changing is the alcohol group is being replaced by a halogen. And we have a byproduct of water. The next part of the question is a practical question. It's given us a lot of information, some volumes, masses, amount of acid, densities, percentage yield, and it's asking us how the student could obtain a pure dry sample of the halogenoalkane from the mixture in the flask, and it's asking us for the mass of pure halogenoalkane that would be expected. So you might want to read this question a few times before you decide what to do first. I've chosen to do the calculation first just to get it out of the way. So the first thing I'm going to do is the moles of the alcohol. And I'm going to use the mass given and do that over the molar mass of the alcohol. So 7.7 over 74. That's what this alcohol adds up to. And I get 0.104 moles. Now, this equation is a 1-to-1. So the moles of alcohol equal the moles of the haloalkane or halogenoalkane. We've got the percentage yield, 76% is expected. So I'm going to do 76% of this amount of moles to get my actual moles. Then I'm going to convert that into a mass so that I can answer the question, because it's asking for the mass of this. So moles times molar mass, I get 7.32 grams. Now I've done the calculation, I'm going to look at the practical bit. It's asking how we can obtain a pure dry sample of that haloalkane. And we have to use all the information we're given. Here the densities are important. And we have to bear in mind these are all liquids. So we're going to do a liquid-liquid separation. And we have to identify what's going to be in the top layer and what's going to be in the bottom layer if we want to get high marks in this question. It's out of 6 marks, and this question is one of those levelled ones with the different bands. And it's the fine details like what's in the different layers, what you're going to use as a drying agent, and what temperature your product will come out at when you do the final distillation step. So you're going to make use of this boiling point at the end as well. So based on the densities given, the HCl has a higher density. More dense things will go to the bottom. So we're going to say the HCl will be in the bottom layer, that is the aqueous layer, and the organic layer will contain our product and will be in the upper layer in this experiment because of these densities. So we're going to use this separating funnel to separate the 2 layers, the aqueous, so the acid, from the organic product that we want. So this acid one, this lower layer, we can just run out and discard. After we've done that and we've ran our organic layer into a clean conical flask, we need to add a drying agent, and we need to give an example if we want good marks. So something like anhydrous calcium chloride or magnesium sulfate, some kind of anhydrous salt. And this drying agent, what that does is it removes any water that's left over. And then we've got one last purification step, and that is distillation, and our fraction, our product, will come out at its boiling point, which is 50 degrees. Next question, compounds A and B are structural isomers of this. Compound A is a secondary alcohol. What is its systematic name? So you might want to draw this and have a go in pencil somewhere along the side to see what looks right. But we've got a 4-carbon chain, so it's going to be some kind of butanol. Secondary alcohol, that means if you've got a 4-carbon chain that the OH group must be on one of the second carbons, so one of the middle ones. So the systematic name of this is going to be butantuol. Next question, compound B is a branched primary alcohol. It's reflux with the acidified potassium dichromate as an oxidizing agent. Write the equation for the reaction that takes place. Use structures for organic compounds and capital O in square brackets for the oxidizing agent. So we draw this thing for compound B from here. We're going to reflux with acidified potassium dichromate. It's a primary alcohol. We're refluxing, so that means we're generating the carboxylic acid, and we need excess oxidizing agent, so we're going to do 2 lots of this. We write our conditions over the arrow, potassium dichromate and acid. This slash means it's a mixture, so it's acidified. Refluxing it, and we convert this OH group into a carboxylic acid group, and we've still got the same number of carbons and everything. And we have a byproduct as well to make the equation balanced, and that is a molecule of water. Now this equation, you could have done it skeletal, you could have used structural formulae as well, which would have been the CH3, CH, and so on. And you get the marks for correctly drawn reactant, correct product, and the third mark for 2 lots of the oxidizing agent and water as a byproduct.